किसी ने कुछ बोला क्या? Okay, so today we will talk about isomorphism. So what is an isomorphism? By definition, it is a linear transformation which is 1, 1 and on 2. So let me formally define it. Let V and W be vector spaces over the same field. Over the same field. क्या कह रहे हैं? किसी ने कुछ बोला? हेलो, अनुराग भारती, क्या आपको मेरी आवाज सुनाई दे रही है और क्या मेरा स्क्रीन विजिबल है?
तो स्क्रीन विजिबल है लेकिन वॉइस थोड़ा बीच में आज ब्रेक हो रही है आपकी।
सबके साथ ऐसा है? प्रिया, आपके साथ भी ऐसा है?
नो सर।
आवाज क्लियर है?
यस सर।
ओके, साक्षी कुछ बोल रही हैं आप? आपका नेटवर्क खराब है साक्षी। Okay, so I was defining isomorphism. So we have two vector spaces over same field, a linear transformation T from V to W is said to be isomorphism, or we can say a linear isomorphism. If T is bijective. T is bijective means it is 1, 1 and on 2. Okay. So if we have an isomorphism between two vector spaces, then we say V is isomorphic to W. Say V is isomorphic to W. So what does this mean? This means V and W, they are same as a vector space. As I said, they may be different, but as a vector space, they are same. So we will see when two vector spaces are isomorphic, then their dimension is same. Okay, we will prove this. So suppose we have a linear transformation T from V to W and onto linear transformation, a bijective linear transformation, say is a bijective linear transformation, that is, it is an isomorphism. Okay, then what can you say about T inverse? The set theoretic inverse of T. So you all know every bijective map, every bijective function is invertible. Okay, you can talk about its inverse. What can you say about T inverse, whether it is linear or not?
Linear.
Is bijective, then there exists inverse.
Is T inverse linear? So let's answer this. So in fact, yes, T inverse is linear. So how do we show this? कोई बोल रहा, अंशु राज, आप कुछ बोल रहे हैं अंशु? अंशु राज, आप कुछ बोल रहे हैं क्या? ओके, आपको किसी को कुछ बोलना हो, कुछ मैसेज टाइप करना, तो व्हाट्सएप में टाइप करो, जिससे कि मैं उसको देख पाऊंगा। अगर आप चैट बॉक्स में लिखेंगे तो मैं उसे देख नहीं पाऊंगा टाइम पर। ओके, अगर आपको कुछ लिखना है, कुछ बोलना है, तो उधर बोलिए, जिनके पास आवाज क्लियर नहीं आ रही है, क्योंकि उनका नेटवर्क बहुत डाउन है और जब वो बोलते हैं तो मुझे समझ में नहीं आ पाता क्या बोल रहे हैं और इससे डिस्टरबेंस भी होता है। तो आपको कुछ पूछना है तो आप टाइप कर दीजिए ग्रुप में, मैं देख पाऊंगा उसको। ग्रुप में मीन्स व्हाट्सएप ग्रुप में। Is T inverse linear? Let's see whether it is linear or not. Take alpha in the field, so it is an scalar, and x and y in v, no, in w. Okay, then let's see what alpha x plus y T inverse will be. So since x and y are in w and t is bijective, means t is onto, so for x and y there exists v1 and v2, so there exists, say, v1 such that t v1 equal to x, there is y, for y there is v2 such that this, okay. So from here what you get, t inverse alpha x is t v1, y is t v2, and you know t is linear, so this is nothing but t of alpha v1 plus v2. But you know, for a function f, okay, for a function f and f inverse, f dot f inverse is identity, which is same as f inverse f. Okay, you know this. So since t is also a function, so t inverse t is identity alpha v1 plus v2, so you will get alpha v1 plus v2. But by definition, this v1 is t inverse of x and v2 is t inverse of y. So we have shown that t inverse is linear. It is bijective. Therefore, t inverse is also an isomorphism. Okay. Any doubts so far? Any
No,
question? Okay. Good. So let us set up all vector spaces over a field. Okay, and then we define a relation. So we define a relation V if and only if V is isomorphic to W. Okay, so in the set of all vector spaces, we define a relation such that V related to W. It is true if and only if V is isomorphic to W. So what can we say about this relation? So if this is true, then this is an equivalence relation. Okay, so have you seen equivalence relation previously? Have you seen this? क्या आपने equivalence relation के बारे में पढ़ा है?
Yes, sir.
Yes.
Okay, so क्या होता है equivalence relation, बताइए तो क्या प्रूव करना पड़ेगा?
Sir, we
Number first, reflexive,
or second symmetric, third transitive.
okay, symmetric and transitive. reflexive means for every vector space, for every vector space, V is related to V is isomorphic to itself. Okay. What is second symmetric means given if V is isomorphic to W, then W is isomorphic to V. Okay. And third one, if V is isomorphic to W, W is isomorphic to say Z, and W is isomorphic to say Z a vector space. Okay, then V is
P
isomorphic to
isomorphic
Z.
to Z.
Okay, so how do you see one? So one is clear from the identity linear transformation. So identity will work for reflexivity. For symmetric, if T is isomorphism, then you know T inverse is also isomorphism. If this is isomorphism, then you know T inverse from W to V is also isomorphism. Correct? This will prove symmetry. So how do you see this last one, transitivity? So if you have two, T1 from V to W and T2 from W to Z, so how will you prove that V is isomorphic to Z? Which isomorphism will you take? If these two are isomorphism, then please tell me. Then what you have to show? V is isomorphic to Z means you have to show a linear transformation which is bijective from V to Z. Okay. So you know composition of two linear transformation, composition of two functions. So T1 composed with T2. Okay. So first T1 will go from V to W, then apply T2, T2 will bring it to Z. So this is also a linear transformation, is a linear isomorphism. So prove this. So proving this is linear will be okay. It is an exercise for you. Try to prove it. You have already seen that if you have two linear 1 on 2 function, then their composition is also 1 on 2. Okay. So T1 is 1 and on 2, T2 is 1 and on 2. Its composition is 1 and on 2. This you have already seen in your intermediate class. Okay. So that part will be easy. The only thing that is to prove is of T1 is linear. So for this, what you do, take alpha scalar and x and y from V. Okay. So then you know Tx will be in W, Ty will be in W. Okay. So now prove T2 of T1 alpha x plus y. This is by definition T2 T1 alpha x plus y, which is T2. This T1 is linear transformation. So this is T1 alpha x plus T1y. So since this is now this T2 is also linear, so this is alpha T2 T1x plus T2 T1y. So this is T2 of T1x plus T2 of T1y. So you are done. Okay, so you have shown that this relation isomorphism is is equivalence relation. Okay, let's see some more example. Okay, if you remember the vector space, we have proven that the set of all polynomials polynomials with real coefficient of degree less than or equal to n is a vector space. Okay, so this vector space of all polynomials with say real coefficients of degree less than or equal to n, and union take this union 0, okay, with this 0 matrix, sorry, 0 polynomial. So with 0 polynomial. So this is a vector space. This is a vector space. Can anyone tell me its basis? What is its basis? Its basis. Hello?
One, yes, sir.
1
x square up to x to the power n minus 1.
to the power n, because less than or equal to, less than or equal to. Okay. So this is so it is an n plus 1 dimensional vector space. So this is an n plus 1 dimensional vector space. So now let us take, so any polynomial p can be written in this form. P is something like this: a naught plus a1x plus a2x square and plus an xn, where these ai, these are real numbers. Okay, this is a polynomial. And so you know this p is in fact a linear combination of these basis vectors. You can see this. So now we define a linear transformation. First we define a function, and we will see that in fact this is a linear transformation. T from V to Rn given by T of P as a naught, a1, an. Okay, where P is as above. P is as above means ai x to the power I0 to n. Okay, it is easy to see that this is 1 1, T is 1 1, T is in fact onto, and T is linear. So you can verify this. How will you verify? You take any alpha in R, okay, take a polynomial P, take another polynomial Q, say Q is summation Bi xi, I runs from 0 to 1. So what is this sum? This will be alpha ai xi plus summation bi xi. Oh, xi. So this will be summation alpha ai plus bi xi. This is again a polynomial, and by definition this is alpha a naught plus b naught comma alpha a1 plus b1 and so on, alpha an plus bn. And you see, you can write it as alpha A naught to An plus B naught to Bn, and this is Tp and this is Tq, alpha Tp plus Tq. So T alpha P plus Q is alpha Tp plus Tq. Therefore T is linear. Do you get this? समझ में आया? कैसे प्रूव करेंगे? Hello?
Yes, sir.
Yes.
कुछ लोगों की आवाज नहीं आ रही बिल्कुल भी, मैं समझ नहीं पा रहा हूँ. आप लोग बोल रहे हैं और मुझे नहीं पता चल रहा आप क्या बोल रहे हैं. ओके, मैं एज्यूम कर रहा हूँ कि ये ठीक है. जिसे मेरी आवाज सुनाई दे रही है, क्या वो बोल सकता है कि ये ठीक है या नहीं है?
यस सर, सही है।
ओके, ठीक है. So what we have seen, this means V and so this T is isomorphic. This means V and Rn plus 1, they are isomorphic. V and Rn, they are isomorphic. So let's see, let's write like this: V and Rn plus 1 are isomorphic. So you see, you know that dimension of V is n plus 1. You have seen it here because in its basis there are n plus 1 vectors, and you know dimension of Rn plus 1 is n plus 1. Okay, so dimension of V is n plus 1, and which is same as dimension of Rn plus 1. So this is not a coincidence. In fact, it will be always true. Whenever two vector spaces are isomorphic, they are of same dimension. Okay, let's see another. So it's in fact an exercise for you. And let us take, say, M cross N matrix. Take N cross M matrix, real matrix. Okay. So we will prove that this is in fact isomorphic to Rn plus Rn cross M. So how will we do this? Take a matrix and take a matrix of order n cross M. So a matrix of order n cross M is like this: A1M, then A21, A2M, AN1, ANM. Okay, what we do, we define a linear transformation. You have to show that this is a linear transformation from here to n cross M. Okay, so how will you define? T of this matrix is in fact this vector A11 to A1M, then A2M, 2 2M, second row, then third row, then fourth row, and so on at the end, nth row. So how many total vectors are there? Total nm vectors are there. Okay. So this is this vector, this sits in R n cross M. Okay. So it is easy to see that T is linear. T is linear. So it is an exercise for you, so that T is linear and T is bijective. This is also an exercise for you. So this means what you have proven, that the vector space of n cross M matrices is isomorphic to Rn cross M. So this means you know what is the dimension of R n cross M. This is n cross M. And since these two are isomorphic, therefore this will be dimension of Mn cross Mr. Okay. We have not yet proven that when two vector spaces are isomorphic, their dimension is same. We will prove it in a moment. Okay, any doubt? Hello?
No, sir.
Okay. No, sir. Okay, then good. Let's move ahead and let's see a theorem. Then our main theorem will be, you can prove our main theorem by your own. So theorem is, suppose we have a linear isomorphism, means T from V to W be an isomorphism, okay, and one more thing, let this be an isomorphism. Then TVI I1 to N is a basis of W whenever Vi is a basis for any basis one to N of V. So suppose, and vice versa, and vice versa. Okay, this means if this is true, then T be an isomorphism. Okay, T will be an isomorphism. Let's say converse is also true. Converse is also true. So this means if this condition is satisfied, then T is an isomorphism. Okay, so what is going here? So we have an isomorphism from T.
और अगर डायमेंशन इक्वल है तो आइसोमॉर्फिज्म होगा, क्योंकि इनडायरेक्टली हम कहा वही रहे।
अगर आपने क्या बोला, अगर
सर अगर आइसोमॉर्फिज्म होगा तो हेलो, अगर आइसोमॉर्फिज्म होगा तो डायमेंशंस इक्वल होगी।
हाँ, ये अभी हम प्रूव करेंगे।
यस सर,
ये प्रूव करेंगे अभी। अगर दोनों आइसोमॉर्फिक हैं तो उनकी डायमेंशन सेम होगी। अभी हम इसको प्रूव करते हैं, ठीक है। और ये मदद करेगा, ये यहाँ से आपको समझ में आ जाएगा कि सेम चीज है। अगर वी आई की बेसिस वी की बेसिस है तो इसके पास डायमेंशन n है, ये देख रहे हैं। और वही बेसिस बन रहा है किसका, w का, तो वो भी कहने का मतलब है कि w की भी डायमेंशन क्या है, n है। करेक्ट? इस थ्योरम की ही कोरोलरी है। तो अभी हम इसको प्रूव करते हैं, तो इसका मतलब हम प्रूव कर पाएंगे कि अगर दो वेक्टर स्पेस है, यहाँ फाइनाइट डायमेंशनल वेक्टर स्पेस है, ये दोनों फाइनाइट डायमेंशनल है। देखो, अगर मैं यहाँ पर कह रहा हूँ कि ये vi from 1 to n एक बेसिस है, तो मीन्स इट इज ए फाइनाइट डायमेंशनल वेक्टर स्पेस। करेक्ट?
यस सर।
Okay, so let's do this, and in fact this is if and only condition. Okay, so prove करते हैं। So what we assume T is an isomorphism. So T is an isomorphism, number one, and assume that Vi I from 1 to n is a basis of V. Okay. So what is your claim? Claim is you want to prove that TVI I from 1 to n is a basis of W. So what you will do is you will prove that TVI is linearly independent and it spans
And
W, correct?
yes, sir. Yes, sir. Spanning or LI.
So then you can say TVI is the basis of W. So let's first prove why TVI is linearly independent. So for proving linear independence, so what you do, you take a linear combination and say it is 0. Okay? You know T is an isomorphism, means it is a linear transformation. So using linear transformation of T, we get this. Is it correct? So what do you
0 को T of 0
यहाँ
भी
से क्या कहोगे? 0 को T of 0 भी लिख सकते हो, बहुत बढ़िया. Since T is isomorphism, it is 1 1. Okay? Since T is isomorphism, T is 1 1.
yes.
Since T is isomorphism,
इक्वल हो जाए
वो किसके इक्वल हो जाएगा?
वो
ये किसके इक्वल हो जाएगा? 0 के. और यहाँ से क्या मिलेगा आपको? This implies because this is linearly independent. ये basis था linearly independent होगा. This implies alpha 1 equal to 0 equal to alpha 2 और ये सब 0 है. ठीक है? So we have proven that TVI is linearly independent. And why does it span W? TVI spans W. Second part, TVI 1 to n spans W. For this, what you do, you take any W from capital W. Okay, this be arbitrary. Take arbitrary W. And you know T from V to W is surjective, is onto. Okay. So this means there exists V in V such that TV equal to W. Okay. But this V is a vector, since V is vector in capital V, small v can be represented as a linear combination of Vi, because Vi is a basis. Okay, you replace this V by this linear combination in TV, so this means TV equal to T of alpha I Vi. What you get is summation alpha I TVI. Okay, so this means, so T and TV is W. TV is W. So W can be represented as a linear combination of TVI. This implies TVI I from 1 to n spans W. So you are done. Okay. So this means TVI is the basis of W. So how will you prove converse part? So assume that TVI is a basis whenever Vi is the basis of V, then you have to prove T is a linear isomorphism. Means T is linear transformation. You know this, T is linear transformation. How will you prove that it is bijective? So you have to show T is 1 1 and T is onto. Okay. Conversely, assume that TVI I1 to N is a basis of W for any basis, VI I1 to N of V. So you have to prove T is 1, 1, and you have to prove T is on 2. Okay, how do you prove T is 1, 1? You prove what you prove, kernel T is 0. You know, for any 1, 1 linear transformation, kernel T is 0. Okay? Hello?
Yes, sir.
So take V in kernel of T, and since Vi is the basis of V, we can be represented as alpha Vi. So 0 equal to TV equal to, so since V is in kernel T, so TV is 0, but you can write this as summation alpha IVI, so which is summation alpha I TVI. But you know TVI is also a basis. So these alpha i's are 0. This implies alpha 1 equal to alpha 2 equal to alpha n. These are 0 because TVI is basis. This means V is 0. So you have proven that kernel of T is 0 and you are done. T is 1, 1. So how do you prove it is onto? So for onto, what you have to do, for any W in capital W, you have to produce a vector V in capital V such that TV equal to W. But this is easy. How? Okay, let's see how will we do this. Since W is a vector of W and TVI is, this TVI is the basis of capital W, this means this small w is same as a linear combination of TVI. T is linear transformation, you get T of summation alpha I Vi. And you know these Vi, these are vectors in V, so this belongs to V. Call this small v, so you get, so this is the preimage of W. So call it small v, so you get TV equal to W. Correct? Any doubt? Hello. Okay, so ये ठीक है? So once T is
Yes, sir.
bijective,
Yes, sir.
we already know T is linear transformation, therefore it is an isomorphism. So corollary, any two isomorphic vector spaces have the same dimension. Okay? Correct?
Yes, sir.
So you have proven this. How? So since say two vector spaces V and W, they are isomorphic, means there exists an isomorphism T. Suppose this is isomorphism. Okay, and say assume dimension of V equal to n. So this means V1 I1 to n is a basis of V. Then from above theorem, TVI I1 to n is a basis of W, and it has n vectors, so therefore dimension of W is n. So we are done. So now the corollary. Every n-dimensional vector space over K is isomorphic to Kn. So we have already proven this. So we know dimension of Kn is n, and vector space which is n-dimensional will be isomorphic to Kn. We have already proven this, but we have an independent proof as well. So let's see an independent proof of this, and it is easy. देखो यहाँ पर हमने ये पहले प्रूव कर चुके हैं एक तरह से. यहाँ पर कहाँ चला गया पेज? ये देखिए हम क्या कर रहे हैं, एक बेसिस हमारे पास थी, किसी भी वेक्टर को लीनियर कॉम्बिनेशन के फॉर्म में लिख पा रहे हैं, ठीक है. और लीनियर ट्रांसफॉर्मेशन, लीनियर आइसोमॉर्फिज्म कैसे? टी ऑफ पी इज ए नॉट, ये जो भी कोफिशिएंट हैं उनको हम ये आर एन में आ जा रहे हैं, ठीक है. सेम यही प्रोसेस आपने, यही टेक्निक यूज करनी है इसके प्रूफ में. So assume that we have a vector space of n dimension. Let V be an n-dimensional vector space over K. Okay, and it has a basis. Since it is n-dimensional vector space, it has a basis. Suppose B, which is U1 to Un, be a basis of V. Okay, now we define T from V to Kn. So how do we define? Okay, we will map TV to a vector of Kn. So what that vector will be? Let's see this. So this V belongs to capital V. You know, U1, U2, Un, these are bases of V. So V can be represented uniquely as a linear combination. So alpha 1 U1, alpha 2 U2, alpha n Un. And these alpha I, they comes from K, correct? Hello?
Yes.
So what, how will you define T? T will be alpha 1, comma alpha 2, comma alpha
2.
n.
Yes.
Okay, where like this. So it is now an easy exercise. You have already proven above that this T is linear and bijective. So prove this. This is an exercise for you. Okay. So this means we have shown that any n-dimensional vector space is in fact isomorphic to K to the n. So now a question for you. So you all know R over R is a vector space and its dimension is 1. Okay. R2 over R is also a vector space and its dimension is 2. You also know R over Q, where Q is the field of rational numbers. This is a vector space. is a vector space. Okay, is R Q finite dimensional? Is this finite dimensional? Hello? Have you seen countability, uncountability? Countable number, uncountable, infinite set, finite set, countable set, uncountable set. क्या आपने देखा है ये पहले? हेलो?
यस सर, बट केवल डेफिनेशन ही, मतलब ज्यादा अच्छे से नहीं, केवल डेफिनेशन ही
अच्छा,
देखी।
ओके, ये इसका आंसर आपको ढूंढना है, ठीक है, और इसके लिए आपको काउंटेबल अनकाउंटेबल की जरूरत पड़ेगी, ठीक है। तो दिस इज एन असाइनमेंट प्रॉब्लम, सारे लोग इसको सर्च करेंगे, ठीक।
ओके सर।
ये बहुत इजी है। अगर ये फाइनाइट डायमेंशनल होता तो क्या होता, इसको रिड्यूस कर देते हैं दूसरे पार्ट में। अगर ये फाइनाइट डायमेंशनल होता तो क्या होना चाहिए था, फिर से ऊपर पढ़ देखते हैं, ये थ्योरम है। एवरी n डायमेंशनल वेक्टर स्पेस ओवर k इज आइसोमॉर्फिक टू kn। दिस इज ए वेक्टर स्पेस ओवर q, और ये फाइनाइट डायमेंशनल होता तो किसके आइसोमॉर्फिक होता?
तो आर के आइसोमॉर्फिक होने,
नहीं
आर
भैया,
को
फील्ड क्या है यहाँ पर? फील्ड क्या है?
फील्ड क्यू है।
q,
क्यू
तो किसके आइसोमॉर्फिक होना था? q।
क्यू एन।
So if it is finite dimensional, this means if it is finite dimensional, if it is finite dimensional, then from above theorem, from above corollary था वो, corollary R is isomorphic to q to the power n for some n in z plus, correct? Okay,
यस सर।
क्या आपको मालूम है कि R कैसा है, काउंटेबल है कि अनकाउंटेबल है? R is a countable set or uncountable set? And what about Q? Is Q countable or uncountable? ओके, अब यहां से वो काउंटेबल और अनकाउंटेबल में आ गया, ठीक है। तो इसको आपने देखना है, इसके बाद आपको आंसर बहुत इजीली पड़ जाएगा। अगर ये आइसोमॉर्फिक है तो मैं क्या कर रहा हूँ, एक बाइजेक्टिव मैप दे रहा हूँ फ्रॉम R टू QN, बाइजेक्शन। क्या ऐसा होगा? इज इट ट्रू? दिस इज द क्वेश्चन, और ये बहुत इजी क्वेश्चन है अगर आपको काउंटेबिलिटी और अनकाउंटेबिलिटी के बारे में मालूम है। अगर नहीं है तो आप उसको पढ़िए, मालूम नहीं है तो पढ़िए और फिर इसका आंसर दीजिए, ठीक है। ओके, एट द लास्ट, one last thing, last theorem. So let V be a finite dimensional vector space let T from V to V. Now we are taking a linear transformation between V to V, okay, itself. This is a linear transformation from V to itself. Be a linear transformation, then the following are equivalent. Following are equivalent. Number one, T is an isomorphism. So isomorphism means T is linear transformation and T is 1 and onto. Second one, kernel of T is 0. Third one, image of T is V. So you say this is bijective, this is 1 1, this is onto. Both are, means all three are same. If T is a linear transformation from V to itself. Okay, so in a finite dimensional vector space, any linear transformation T from V to itself, if it is 1 1, then it is onto. If it is onto, then it is 1 1. So this same thing. So let's see a proof of this, and proof is easy. I will just tell you how we will do this. So suppose T is 1 1, sorry, T is an isomorphism. Okay, assume 1, T is isomorphism. So this means T0 is 0, this is T0 is 0 and T is 1 1. So this means for any V in kernel T, TV equal to 0, which is T0. Since T is isomorphism, T is 1 1. This implies V is 0, this implies kernel T equal to 0. Okay, ये हम पहले प्रूव कर चुके हैं. So it is okay. So first part done. Okay. Now second thing, assume 2 and we will prove third. Assume 2. So here kernel T equal to 0. This means dimension of kernel T, that is nullity. So nullity of T is 0. Okay, correct? You have proven yesterday that for this T, dimension of V equal to rank of T plus nullity of T. So this implies dimension of V is same as rank of T, means dimension of image of T. Okay, and image of T is a subspace of V. Is a subspace of V. This implies V is image of T, and we are done. So here what I am using, so here I am using a simple exercise for you. Suppose W is a subspace of V and dimension of W equal to dimension of V, that V equal to W. The last thing is also easy. Using rank nullity theorem, you will prove this. So what you have to prove? You have to show that this is onto, you have to show that it is 1 1. Okay, so I'll leave this for you because it is time, and I have even given you a proof of this in your notes. If you have any doubt, please ask. So I will stop sharing this. Any question, comment?
No, sir.
Okay, then drop your attendance.
Thank you.